Okay, so it's my great pleasure to welcome everybody and see such a great turnout for this third distinguished seminar series that we started in the Department of Civil Environmental Engineering. So this series is sponsored by the department, the CE department, and the Chiang Mai Funds. And today's speaker is Professor Harry Swinney from University of Texas. And it's my great pleasure to introduce him. He is a member of the National Academy of Science, fellow of the American Academy of Arts and Sciences, the American Association of the Advancement of Science, the American Physical Society, and SIAM, which is the Society of Industrial and Applied Mathematics. He had made seminal work in nonlinear dynamics, including instabilities, chaos, pattern formation, with various applications in fluids, basically solid, granular, biological systems, and so on. And I'm really excited to hear the talk, Universality in Nature, which is very broad, that will hopefully bring us through the whole panel of applications. He is also was awarding the American Physical Society a Fluid Dynamics Prize, the Society of Industrial and Applied Mathematics Jürgen Moser Lecture, and the Boltzmann Medal of International Union of Pure and Applied Physics. So without further ado, I will leave the floor to Professor Harry Swinney.
Thank you very much. It's an honor to be here, a pleasure to be here. I am a member of a physics department, as was mentioned, but my roots are in engineering. My grandfather was a civil engineer. My father was a civil engineer. But the person who I really looked up to was another engineer, my uncle, who was an electrical engineer, who told me great stories about the years when he was here at MIT during World War II as an instructor in the rad lab. And so I aspired to be an electrical engineer and went into college with the plan to get a degree in EE. But along the way I strayed and got a degree in physics, but also along the way I had an internship in engineering and found it very exciting. And I graduated and I got a job as an engineer, electronics engineer. And it was very exciting, challenging problems, lots of toys to play with, and deadlines to meet. And I did that for a bit of time. And then I went to graduate school in physics. After graduating in physics, then I've been various places and had collaborations with a number of people, mostly engineers. So I have a foot in engineering as well as physics. So I will talk today about a variety of systems that at first glance sometimes look very different, but are at times found to be described by the same underlying mathematics. And towards the latter part of my talk, I'll illustrate this with some results, this perspective from results from our laboratory in Texas, and work there is, of course, done by the students and postdocs, and I should thank them, and it goes without saying, it takes some funding to do it, so I thank the agencies which have supported this work. So I want to start back in 1685. Young Isaac Newton was an instructor at Cambridge University, and there was a plague in London. 25% of the people in London died, and they closed Cambridge University. And Newton went home for the year. The university was closed for a full year, 1865 to 66. And he said to his friends later on, that's where he began to think about an apple falling from a tree. He had a lot of time to think. And he said, watching the apple falling from the tree, there must be some force that's pulling it down. And it must be, what could it be other than the earth pulling it? And if the earth is pulling it, why doesn't the apple fly to the side or the other direction, right or left? Well, it must be pulled to the center of the earth, as though all of the mass of the earth were concentrated at the center and it was pulled down. And then if the earth was pulling the apple down, wouldn't the apple pull the earth up? Wouldn't it be symmetric? And he wrote the equation we all know that the force is proportional to the product of the masses. And he conjectured the dependence and separation would be as inverse r squared. So he thought about this problem, and he said, as the next 2 decades pass, that if this force applies to the apple and the earth, maybe it would apply as far out. That distance r could be as far out as the orb of the moon and describe the orbit of the moon. And later on, he had his momentum equation. The rate of change of momentum is equal to the net force, we all know. And that's the rate of change. Now, to solve that, if you know the force, you have to integrate. So he invented the calculus and integrated the equation and said, well, let's apply it to the orbits of planets. And he obtained the laws for planetary motion that Kepler had found early in the 17th century by looking at the data from Tycho Brahe's lab, by just analyzing data and fitting it and finding the elliptical orbits and the other 2 laws that Newton then derived, given the force law and given the momentum principle. So we have a fundamental force, the gravitational force, a universal force, which, as Newton said, surely it must apply to all masses in the universe. Any 2 masses, no matter how far apart they may be or how close they may be, would be described by this force law. Then, in the following century, people began to study the forces between charges, and this culminated with the work of Augustin Coulomb, who found a law for 2 charges at rest, Coulomb's law, which has the same form as Newton's law, except you replace the masses with a charge. And then it was found in the next century that if you look at charges that are moving, as Faraday did in the early 1800s through the middle of the century, you find moving charges produce magnetic fields. So electricity and magnetism are tied together. And this led to the second of the fundamental force laws that were put together by Maxwell, building on the work of many people in the 19th century. And as you know, like charges repel, and unlike charges attract one another. Now, Maxwell put the equations for the electric and magnetic fields together and obtained a wave equation and predicted that moving, oscillating charges would produce radiation, a wave. And that was detected, there you have it, light. Was detected a decade later by Heinrich Hertz, who produced and detected electromagnetic waves. And then we go into the 19th century, where it was realized and demonstrated that atoms, a fundamental building block of atoms, actually exist. Of course, in the work of Maxwell and Boltzmann, they were assumed to exist and collide, and they developed statistical mechanics, and there was a lot of reason to believe there might be a small indivisible particle called an atom, but it wasn't really demonstrated until 1908 or 9, after Maxwell had given up in despair because of the pushback on some of his ideas of people who thought atoms were just a mathematical construct, that they didn't exist in reality. And Boltzmann had some difficulty in taking criticism, and he committed suicide, as we know. And then it was really shown atoms exist. And then the nucleus was discovered by Rutherford, and moved forward, understanding the nucleus is a very small particle compared to 100,000 times smaller than the atom. And we want to understand the forces in the nucleus. And there was work done with the accelerators that were built beginning in the 1930s and moving forward, particularly in the 50s and 60s especially. And by the 1970s, there came to an agreement on some understanding of the force that holds the nucleus together. The strong force, which is 2 orders of magnitude larger than the electromagnetic force at distances the size of the nucleus. It's different in functional form on distance in that its range is only 10 to the minus 15 meters, whereas electromagnetic and gravitational forces are infinite ranged. But within this range, this force is very strong. It can hold 2 protons in the nucleus close to one another, 10 to the minus 15 meters apart in the helium nucleus, for example. Many people contributed to understanding of the nuclear strong force in the 1970s and earlier, but it culminated in the 70s. And also, at that time, concurrently, there was an understanding that there's a weaker force that's involved, that is involved in radioactive decay and fission of nuclei. And it extends over even much smaller distance, a distance of 10 to the minus 18 meters. And it's much weaker than the strong force, 1,000,000 times weaker than the strong force. But it's important in certain processes. And some of the work on the nuclear weak force was done here at MIT in the 1960s, late 60s, by Steven Weinberg when he was on the faculty here, before he moved to Harvard in the 70s, or before he moved to the University of Texas in 1980 or so. So we have the 4 universal forces, and there are, as far as we know, no other fundamental forces. Every few years there will be an experiment that reveals evidence for the 5th force, and there's a lot of excitement and articles in the New York Times and so forth, but some flaw in the experiment or interpretation is discovered, and so these forces remain as the fundamental forces, universal forces in nature. Now, if you go to high energies, higher than available at the Large Hadron Collider in CERN, you see gradual unification of these forces into, let's see, what is it? Oh, there we go. So we've already seen the electricity and magnetism was unified into the electromagnetic theory of Maxwell, and then work on the weak force together with electricity and magnetism, work by Steve Weinberg, Shelley Glashow at Harvard, and Abdus Salam, led to understanding that at higher energies, that these forces, electromagnetism and the weak force, would be unified into electro-weak force, and that was subsequently verified in experiments, and they got a Nobel Prize for that. And at yet higher energies, so the energy at the LHC right now is about up to 13,000 GeV. So we're a long way away from the predicted unification of the electro-weak force and the gravitation force into the next electronuclear force. And then ultimately, energies that will not be achieved in our lifetimes in the controlled laboratory, maybe in cosmic rays, but is the grand unification, something Einstein aspired to understand. And then you have the theory of everything. That is the theory of everything as far as forces are concerned. But even if you know these forces precisely, you understand them completely, that doesn't tell you anything about the behavior of large numbers of atoms. You take a cubic centimeter of gas in this room, cubic centimeter contains more than 10 to the 19th molecules, and there's no way possible to calculate, even if you know the forces between the molecules precisely, to calculate what's going to happen through all the collisions, what will be the relationship between the different macroscopic properties that describe that fluid, the air. So one must take another approach. So even though it is called the theory of everything, that's the theory of everything you want to know about forces, but not about matter. So much that is not explained by the final theory, as it's sometimes called. So here's just a schematic of molecules that are colliding in a cubic centimeter. Actually, not all the molecules are shown in the cubic centimeter. There's some more, but here. So what is the relationship between the macroscopic properties of the air molecules that are in, say, a cubic centimeter of air? Macroscopic properties like the pressure and the volume, the temperature, or the thermal expansion coefficient, whatever. The first step in this direction happened a century and a half ago, the ideal gas law relating pressure and volume of gas to the temperature T, for N is the number of moles, everyone knows here, and R is the universal gas constant. That is, this is a universal law describing any gas at sufficiently low densities. And they were thinking of gases like oxygen or nitrogen, but it would also apply to a gas of DNA molecules. It's a universal gas law if the density is sufficiently low. Now, if you increase the density, then departures from this law are observed. If you take the pressure, volume, and temperature in this room and see how accurate this equation would be, it's within 1% or so for gas in one atmosphere. But if you increase the pressure, lower the temperature, then it begins to fail. And another equation of state was proposed by van der Waals in his PhD thesis in 1873. And it does a better job when the density is higher, better job than the ideal gas law, as the density increases or lower temperatures. What was observed in the experiments that began in the latter part of the 19th century was that if you look at pressure versus volume, or pressure versus density of fluids at a constant temperature, you obtain a diagram that looks something like this: isotherms for a fluid. Measurements were made for a number of gases in the late 19th century, and with greater precision in the 20th century. And you have, at high temperatures, now this is a plot of just pressure versus density. High temperatures, there's a single phase. You can vary the density, but you never see a change of phase. But at lower temperatures, you have two phases with a meniscus between them. You have a liquid phase and a vapor phase. Well, this has air above it, but it could be water vapor above it in a sealed container. If you get below a certain temperature called the critical temperature, here, this point here, anywhere along this line is at the critical temperature. Below that temperature, you get two phases that coexist: the liquid phase, the high density phase, and the low density phase, the gas. And these curves were obtained for a number of different gases, and they look somewhat similar. And people wonder, is there any universality in the behavior near of the isotherms, the behavior near this critical point? Because the critical point exists for all material, all gases. And more measurements were made, And they culminated in a great step forward in 1945 when Guggenheim put together all the data he could find from different gases on a single curve where the pressure, where the density now is measured relative to the critical density, and the temperature relative to the critical temperature for that substance. Now, the critical temperature for different, fluids here is quite different. For carbon dioxide, it's 31 degrees Celsius and so forth. For these gases, they had different critical temperatures, varying quite a bit. But when you plot them relative to the critical temperature, you have the liquid density data following this curve and the gas data following that curve there. Now, there was a universal theory of phase transitions of gases. It was put forward by Landau in 1944, Landau theory of phase transitions, in which the curve was predicted to be square root as you go in, if you go in that direction, this would be a square root behavior. But this was interesting in that the exponent describing the shape of this curve near the top was clearly not 1/2 rho liquid minus rho gas varies as the temperature minus the critical temperature minus T to the 1/3 power, roughly. Not the square root. And that's a puzzle. Because Landau theory was pretty solid. It was basically a Taylor series expansion about the critical point of the free energy function. And how could that be wrong? So measurements were also made of the magnetization of ferromagnets. And here is the strongest magnetic material that's found in nature, the mineral magnetite. And you look at the magnetization as a function of temperature, and you see as you increase the temperature, as Pierre Curie found, you reach a temperature which is called sometimes the critical temperature, but it's convenient that it's Curie, so it's Curie temperature as well, Tc. Above that, the magnetization is 0. So it dropped, magnetization drops, and it's 0. If you come back down in temperature, then you get the magnetization increasing. So there's no hysteresis in this. In the ideal situation anyway. You have this curve describing the magnetization. Now that looks different from the coexistence curve, but if you take this coexistence curve now and just rotate it 90 degrees and plot it, you see the curves look rather similar. And in fact, the functional form from experiments now, we're moving up to the 1950s and 60s, where there was great interest in the subject of phase transitions. And universality, is there a universal theory that describes the transition of many different materials? And it looked as though within the uncertainty, the exponents describing the shape, mathematical shape of this curve was the same within the experimental era as for one another, but it was different, quite different from the expected result, which was the square root dependence on square root of temperature critical minus the actual temperature. So finally, the subject was addressed by someone new to the field, a particle theorist who was working at Cornell, talked with some of his colleagues in the physics department at Cornell, Ben Whittam and Michael Fisher, about critical phenomena, and they told him about this dilemma that all the classical theories predicted one set of critical exponents characterizing the susceptibility and the coexistence curve in different quantities as you approach the critical point, and the exponent values were quite different from what were observed for different substances. And he used a renormalization group theory which had been developed in particle physics, in which people in condensed matter didn't really understand. It was not a simple theory, but he found for systems near critical points a universal behavior, whether you're talking about ferromagnets or antiferromagnets or fluids or binary liquid mixtures or other systems. He found this behavior. And now it does depend on two parameters, and one is the dimensionality of the system, two-dimensional system, a thin monolayer of fluid would behave differently from the three-dimensional gas, and it does depend on something called the order parameter for the dimension of the order parameter. So a gas system has only two phases, liquid and vapor. And a ferromagnet, if you think of spins all in a material all aligned up or down, has also two possible phases. So a one-dimensional order parameter. But in magnets, you could also have spins which point in any direction. And then you have a different set of exponents. But they were all given by this theory. And for that work, the theory of phase transitions, Kenneth Wilson received the Nobel Prize. So we're talking about systems which are in thermodynamic equilibrium. Phase transitions in systems which are at a constant temperature, uniform temperature. Well, what happens if you drive a system away from equilibrium? In the remainder of my talk, I want to consider systems driven away from equilibrium by the imposition of some gradient. So suppose we have a fluid in a box, and there's a gas or liquid in the box, a fluid in a box, and the bottom is hotter than the top. Now, if the temperature difference is small, the fluid will conduct heat from hot to cold, but there's no mass motion. You have the molecules in the fluid are colliding, but they only affect the nearby molecules. There's no long-range effect. Correlation length is only nanometers in this system. But if we increase the difference in the temperature at some critical value, now we're pushing the system away from the equilibrium state, thermodynamic equilibrium state, and you have the onset of convective motion. And you have heat rising here and falling here. And now you have the motion of a molecule here can be correlated with a molecule very far away. If this is 1 centimeter long, you could look 100 centimeters away and see the effect that these rolls are all the same size, and you could say something about the behavior very far away. You have long-range order that has appeared at a certain temperature difference. Now, there were attempts to describe that transition to convection made by a number of people, but they didn't correspond to laboratory observation. But an experiment was done in the 1920s by G.I. Taylor at Cambridge University on a system of 2 concentric cylinders. Let's say only the inner cylinder is rotating here for simplicity, and the fluid is contained between the 2 cylinders. So we can describe the distance away from thermodynamic equilibrium by some dimensionless number that's familiar to everyone here, the Reynolds number, which we take to be some velocity, characteristic velocity, tangential velocity of the inner cylinder times a distance, which is the distance between the 2 cylinders, divided by the kinematic viscosity. And look at the behavior here as the Reynolds number is increased, as the frequency of rotation of the inner cylinder is increased. And that's what G.I. Taylor did first in a laboratory experiment. So he had the fluid rotating between the 2 cylinders, and he increased the speed of the inner cylinder. And he injected dye to see if he could see the motion of the fluid. And at a certain well-defined rotation rate of the inner cylinder, he saw a transition where you get the formation of vortices that encircle the inner cylinder, and they're stacked along the axis of the cylinders. And there's a characteristic repeat distance, the wavelength, So you have, say, along this black line, this is visualized not with dye, but by putting small flat flakes in the fluid, taking a picture. But it's similar to the pictures Taylor obtained in his 1923 paper. He presented them. But this would say the fluid is flowing in towards the inner cylinder here and outward towards the outer cylinder here. The fluid flows around the little toroidal-shaped vortex. So then, having observed this transition, which occurred at a well-defined rotation rate, Taylor looked at the equations for a fluid, Navier-Stokes equation, and it's easy to obtain the solution when the cylinder is rotating slowly, because you know that for small Reynolds number, small distances away from the equilibrium state, thermodynamic equilibrium, your solution will have the symmetry of the boundary conditions, and you can solve simply and get the only component of the velocity field you have is in the azimuthal direction, and you can solve and find its dependence on the radius. There's no vertical motion and no radial motion. Now you can take that state and imagine that there's an infinitesimal perturbation of that flow and calculate from the equation of motion for a fluid, the Navier-Stokes equation, obtain the equation for that perturbation, and that's a linear equation because you assume the perturbation is infinitesimal. And you can solve that and find the growth rate of the instability, and he found a well-defined Reynolds number at which the instability occurs, and he got this result, where now he rotates more generally both cylinders, and you have the rotation rate of the inner cylinder in this axis, and it's at rest here, and rotation rate of the outer cylinder along this axis. So in this, beyond this point to the right, you have the cylinders here rotating in the same direction. Here, they're counter-rotating, opposite directions. So he first got these red points, which are from an experiment, observations, and then he did this analysis of the stability and found where the perturbation grew, and he obtained these green points, and there's incredibly good agreement. So this demonstrated, really in a very clear way, the validity of the Navier-Stokes equations, and also the validity of the assumed boundary conditions. That is, there's no slip at the inner wall, no slip of the fluid past the wall, and no slip of the fluid at the outer wall, the no-slip boundary. So, as Taylor says, quoting from his paper, these attempts by some people whose names are familiar here, Kelvin, Rayleigh, Hopf, and Sommerfeld, they'd all tried to calculate the point at which a fluid flow would become unstable. He says, I've done it, guys. He's calculated the speed at which a fluid becomes unstable. Okay. Now, 3 decades later, a person familiar to everyone here became interested in an entirely different kind of problem. Alan Turing was interested in how form occurs in biology. How do you explain how a leopard gets its spots? And of course, he was a mathematician. He's not a biologist. He didn't go to the lab. He developed a model in which you have 2 chemical species and there's no fluid flow. These species just react with one another with some rate constant, and they diffuse. Species A with some diffusion coefficient d sub A, species B with some diffusion coefficient d sub B. They diffuse, reaction and diffusion. And now you vary the concentration of these species and see if a pattern might emerge. And he said he found the conditions for this simple model, particular model, where as you varied the concentration of the species, there was a critical value at which a pattern would spontaneously form. And in his mind, he said, this is enough to explain the genesis of form in biological systems. Now that's a statement still under debate, but in some cases it's found that you have Turing-type modifications in actual mice that Kondo has studied in Japan and identified the gene that causes the stripes to move down the mouse. Anyway, he found patterns in a biological system. So there was this suggestion that experiments should be tested on a simple system, not in a biological system, but in a laboratory system. In 1984, I read this paper and became interested in the possibility of doing a laboratory experiment to see a Turing pattern. But how do you build a system which maintains a chemical system, reaction diffusion system, away from equilibrium, sustained state away from equilibrium, and have no flow? Well, we worked in my lab with various designs of reactors that might do this, and came up with this design, which we used for the next 20 years after that, in looking at chemical patterns. So we have chemicals fed into one reservoir that is well stirred, so the chemistry is homogeneous. Concentrations are homogeneous in that reactor. Say it's an oxidizing chemical. Chemical concentrations are homogeneous in this reactor, but the chemicals can diffuse into a gel. The gel prevents mass motion. So you only have reaction of the oxidizer and reducer and diffusion of the chemicals. And we fed in some chemicals, oxidizer and reducer, and looked for the formation, and we discovered, or we observed, Turing patterns. Here's an example. Now, in the Turing theory, there's a relationship between the chemical kinetics, diffusion, and the characteristic length scale for the pattern. And that's shown here, that if you measure the diffusion coefficient, which we did for the chemicals here, and the characteristic time for this reaction, the rate constant, and then calculate the wavelength, and it all fit together. So this is a Turing pattern. And you can see that it is a pattern that forms at a certain critical condition, which you can vary. You can vary the temperature to vary the rate constant and see the transition from a uniform state to a pattern state occur, or you can vary concentrations, see the same way. And the reaction, the transition is non-hysteretic. So you can see the pattern form and the amplitude grow as you move away from the transition. You come back down to the point where the pattern first emerged, and the pattern disappears as you go down. Now let's take another system. And this is one that had long been known. Faraday described it in the 1830s in the appendix of a paper in the Philosophical Transactions of the Royal Society. If you take a pan of water and oscillate it up and down, you see the level of the water remains flat. But if you increase the oscillation amplitude, then at some point you see the emergence of a pattern. So that was seen by Faraday, and the theory was not worked out for 150 years or so, but it works out. And so it's again a stability analysis, and the experiments were done by a number of people testing the theory and finding good agreement with the predictions from a stability analysis, depending upon the thickness of the layer, the frequency of oscillations, and so forth. You can get different patterns, but you see a clear onset of surface waves on the layer of water as you oscillate it, or oil, the fluid, as you oscillate it up and down. Okay. Now, another experiment that looks for the emergence of a pattern, a transition to a pattern, was done with a loudspeaker with some grains on top of it. And just as for a fluid, you see no pattern initially. When you oscillate with small amplitude, the layer of grains remains in the container throughout the whole oscillation cycle. If you get to higher amplitude acceleration, then above 1G, the layer will leave the pan and go up in the air, part of the cycle, and then come and strike the pan. But still, you see no pattern. But if you get up to an acceleration during the cycle that exceeds 2.5 G, we found the patterns emerge. And if the frequency was, low, we'd get square patterns, and here at higher frequency you get the stripe, basically stripe patterns. You don't see the grains of sand here, but we have close-up pictures where you can see one little cross point here where you, in this pattern, this is a snapshot at an instant of time, incidentally. This is a subharmonic pattern. You go 2 oscillations of the container later, you see the same pattern. You go 1 oscillation later, the pattern is just shifted by 1/2 the box size here. And you have the same pattern. But in 2 oscillations later, you get the same pattern exactly. Here are the stripes, or you go up higher in acceleration, you get a hexagonal pattern. So in doing this experiment, it was found for some conditions you could get a local structure which is non-propagating, not like a soliton. It just oscillates up and down subharmonically. So in the next cycle of the container, instead of having a peak, you have a little crater. And then 2 cycles later, you have a peak. But the rest of the whole layer can be flat. And this was studied, Pedro Reis is here somewhere. Hey, Pedro. So this work that was done as part of a project Pedro Reis worked on when he was at City College with Mark Shattuck. And they studied the properties of this granular system. They studied in particular, I think in this reference, it was the velocity distribution of the particles. It was not Maxwell-Boltzmann, deviated from Maxwell-Boltzmann. And they worked it out and showed it very nicely. So you get this localized structure. Well, the pattern formation process that I've described in all of these is now straightforwardly worked out by students in applied math course, where you look at a system away from equilibrium and you look at infinitesimal perturbation of the base state that occurs near the thermodynamic equilibrium. If you just slightly stress a system away from the equilibrium, you get a distortion of the equilibrium state, but one that has the same symmetry. And you look to see whether the perturbation grows or decays. And if you look at the solution of the eigenvalue equation, you get the growth rate, which is plotted here, of an infinitesimal perturbation, would have a dependence on wave number. So you have a characteristic wave number, which characteristic length scale, which first becomes unstable as you increase the distance away from equilibrium. I'm just using Reynolds number here to be a dimensionless parameter that represents the distance away from thermodynamic equilibrium. And here at the neutral stability point, the instability curve just touches the 0 value. So 0 growth rate. And above that, you have positive growth rate and patterns emerge. Now, the eigenvalue, the growth rate, can be complex as well as real. If it's complex, then you get spirals. And here we have, this is a snapshot in an instant of time. You see the core of a spiral here and a core of a spiral here. And now you should see what happens as time evolves. This is a time evolving problem. You see the rotating spiral patterns. And this is an oxidation front in this oxidation reduction reaction. The white is the oxidation front. The two fronts approach one another and then annihilate. These spiral patterns occur in many situations. They occur in some retina. They occur in the heart. It's a real problem in the heart. If your electrical conduction is not as good as it should be from the sinus node down to the pumping chamber of the heart, then spirals can develop, spiral waves instead of straight electrical conduction. These spiral waves form in many hearts every year, and more than 100,000 people a year in this country die from the formation of these spiral waves. So there's a lot of work done here at Harvard Hospital and in medical centers, many places, on spiral wave formation and how to save the people who have this, how to switch back to the normal wave from the sinus node down to the heart chamber. So spiral waves are of great practical interest, and not only in that example, but in others. Okay, oh, I forgot. I was going to, Pedro, could you help me? Let's see, everyone should take a white sheet here, quickly. Let's see, somebody here help me in passing these out. I appreciate it. Just pass them out very fast so every other person or so get one to do a little, it's that part of a talk when everybody is bored and need to have audience participation. Let's see, do you have some here? Okay, here, yeah. Okay, oh, I need one. Okay. So we're going to do, this is a piece of a trash bag, like the one in your office or in your house or apartment or whatever. And most of them have a little tear in one side. That makes it easier. Have a little, just to start the tear. And what we'll do is tear it apart. Let me just start a little tear on one side. Here, we're going to, you see the little, we're not quite ready. Okay. Okay, so if you have a little cut on one side, put that cut up and just tear the sheet apart. Okay, you've all done this. Tearing the wrapper off a CD cover. I guess that's all archaic now. You don't have CD covers. You download, right? Okay, so here, let me see yours. Right? So you look, and you have two pieces, and you look, we're just concerned with the edge of these two pieces. So look at the edge. And I'm going to show something which has this kind of wrinkly shape. Now you see this in the experiments I saw today that have been done in many labs where you have an oil layer between two plates. So here we have an oil layer, and then we have a hole so we can pump some air in the center into the oil layer. And you see that here. Here, the black bubble is a little bubble of air. And if you pump it slowly into the oil, that bubble remains nicely circular. But if you pump it a little faster, what you see is this. And you see something in which a branch grows and flattens at its tip and splits, and does this again and again. And this is a phenomenon seen for many years. The cell is a Healy-Shaw cell that was, Healy-Shaw was the person who did experiments in the 19th century, but this fingering phenomenon was studied particularly by Safman and Taylor in the 1950s. And there's much to be learned and is being studied here, where you see this kind of multi-fingered structure or fractal structure. Now, you take this sheet, which you've just torn in half, and you look at the edge here. Just look at the edge, and what do you see? You see a waviness, right? Now, there it is between the two fingers of Iran Sharon, who was working in my lab. And this project started by his pulling the trash can liner out of my trash can in my office and doing this experiment here, saying, do you understand this? I said, no, I don't understand that. And he said, well, let's study it. And what he was doing something else. I said, but that does look interesting. And what you see, if you look closely, is a big wave, or some big waves. And let's say, take a section 30 millimeters long, you look at it, and now you take a picture with an ordinary camera, say of just 30 millimeters, and let's take just a segment there and blow it up, let's say by a factor of 3.2. And looks kind of like the original picture. And you do it again, and again, and again, and again. So you see waves within waves. You have a fractal structure. This is a fractal. If you go to the supermarket and look at the leaves and the leafy vegetables, look at kale. It looks rather like that, right? So how do we understand this? Well, you can imagine that we take the original sheet and have a grid of dots, a square grid of dots with a certain separation, close together. And now when you tear the sheet, you don't change the distance between the dots that are far away from the tear. But those near, right at the edge of the tear, the separation between two dots is now much larger. In fact, it's about a factor of 2 larger here. But you move anywhere along the edge, and the separation between two dots is the same. The amount of stretch is the same in the distance along the edge. But if you go in from the edge, the amount of stretch is decreased. This is the separation relative to the original separation of the dots. So here it's somewhere between 1.5 and 1.2. So to try to understand this phenomenon, my colleague Michael Marder calculated what would be the shape of a sheet like this where you impose a metric, and impose a metric of different forms. So if the stretch is very large, you get this fractal structure, waves within waves within waves, as you see here. If you have less stretch and you look at the system, you can see maybe 2 characteristic wavelengths, one short wavelength and one longer wavelength. And if there's less stretch yet here, you have only a single wave. Now, the unsolved problem to this day, this was work done more than a decade ago, is how much stretch, what are the necessary and sufficient conditions on this function such that you get a fractal structure? That's not solved. Right? What are the function and its derivatives, say? But you get this wrinkling kind of behavior. Now, we also look at leaves, and you can look at leaves in the supermarket. You see some leaves have a single wavelength along the side, and some have 2 wavelengths, and some have. Kale has, as far as you can see, the fractal cascade all the way down with a dimension about 1.7. But here's a lettuce leaf, and you look at flowers. This is a violet flower petal. You can see the larger waves and waves within it, like here, and then within that wave, others. Okay. So you see, systems which look very different sometimes have very similar, even mathematically similar behavior. These patterns all have the same fractal dimension for reasons we don't understand. Okay, so we're getting close to the end, I guess. So let me go to a different kind of problem, one that is now being studied in many groups around the world. If you have groups of some organism that are interacting, organisms are interacting, then you can have group dynamics. You can have groups of birds form flocks, and fish swim in schools. And suddenly one fish turns and they all turn. You have this collective motion. So you can develop models that of interacting particles and find similar behavior. But how can you understand is this behavior similar in different kinds of organisms? Ant colonies. Or in chemistry, or a number of areas, these particles, nanoparticles with, say, a different catalyst on each side, then in a reacting fluid, then they are propelled because the reaction takes place on one side and will propel them along. And they don't just go randomly like molecules of gas in this air. They move together collectively. And how does one understand that? Or locust swarms or zebra herds, whatever. So experiment was done in London, in Rome, tracking birds, starlings. Several million starlings roost along the banks of the Tiber River every winter. And every night they are seen to form flocks.
10 million starlings flock together to create the most astonishing aerial display in nature.
So they did the most amazing experiment. This group in Rome took a set of cameras and tracked in a flock every single starling. Now, it's three-dimensional and they're flying all, but track every one in a given flock for a period of time. And what they found, looking at different flocks in time, they found if you look at the starling orientation, if starlings are close together, they are oriented in the same direction. But if you move away, even within the same flocks, farther apart, the directions are different. And so what's the correlation length of that orientation? Well, it turns out to be very simple. It's about 1/3 the flock size for flocks ranging in size from 10 to 100 meters. That was really surprising. There's no explanation. I mean, you can make a model in which this occurs, but there are many models of collective behavior, and how does one understand it in a deeper way? Well, we were studying bacteria swimming, and on the surface of an agar gel. And then we said, whatever the behavior is for starlings, it'll certainly be different for the bacteria. We'll have a different universality class that we'll discover. Because bacteria here are in 2 dimensions, not the 3 dimensions of the starlings. The bacteria are at very low Reynolds number, 1 part in 10,000. Such low Reynolds number, then inertia plays absolutely no role. If they stop rotating their flagellum, they stop instantly. There's no coasting. Whereas the starlings are well above Reynolds number 1, so inertia plays a big role, and they can glide, right? So that is another difference. Also, the starlings see one another, and they think their motion in flocks is very dependent on their vision in their brain, the optical system, to help them orient. But bacteria certainly have no eyes. They have no brain, not even a bird brain, you know. So we studied bacteria, and the bacteria that swim. They're little rods, and if you go out here, take a handful of dirt, you'll find some Bacillus subtilis bacteria probably. You can eat the dirt. It's not, well, it probably wouldn't be very good, but they swim. You don't see the flagella. The flagella are very tiny in this TEM, transition electron microscope picture. You don't see it, but they swim. And you can see them, if you look now, they grow on the surface of the gel. And here's a photograph of the bacteria taken through a microscope. And we can see how the orientation varies, and we want to identify them based on their orientation and their speed. So color here just indicates that others of the same color, same bacteria, say that have all these orange arrows, are moving in approximately the same direction and with the same speed. The arrows are the same length and the arrows in the same direction. But bacteria in the same cluster that are far away can be in a different direction. So you can follow them as time evolves, and you see it's a very dynamic situation with bacteria joining the cluster and bacteria leaving the cluster all the time. And if a bacterium is not in a cluster, like this one right here, it's not moving, but a cluster comes along and it'll go along for the ride. So there's great advantage in numbers. If you're together in a cluster, you move much faster, 100 times faster than if you're a single person, single bacterium, excuse me. And that's a good thing if you want to find food or if you want to escape a predator. So we calculated the correlation for these bacteria, and these are the points shown here. And the symbols are for a wide variety of conditions, varying the humidity and varying the hardness of the gel, and the dashed line is for the starlings. So it's the same kind of description. We have no explanation, but it's another example how systems that are very different can have the same behavior and presumably the same mathematical model to describe them. So let me conclude. Universal forces, we've seen phase transitions in systems in thermodynamic equilibrium, have this behavior found by Kenneth Wilson, and the emergence of patterns, and talked about growth processes. Let's see. So beyond the first instability, which you can compute in the way I described, you have no general theory, but you can conduct experiments, numerical simulations, build mathematical models, and the behavior is often seen to be similar or the same, mathematically the same. But unlike systems in equilibrium where you can find a free energy function for a system and the minimum of the free energy, there's no general approach to the description of these systems far from equilibrium. So for the students out there, students present, that's the challenge. That's a hard problem, to understand non-equilibrium systems and their behavior in a general way, to develop a general theoretical approach. And that's where I'll stop. Thank you.
Questions?
Yeah. Yes.
I'm surprised you didn't show the power law of turbulence.
Yeah. There are many examples. Yeah. I had another 100 slides, so I had to. Yes, there are many examples where you could talk about general behavior of systems, particularly far from equilibrium.
Yeah.
So in the formation of this oscillon structure for the vibrated granular thing, how much is that structure dependent on the fact that it is a granular medium?
No,
because the original instability was with a fluid, right?
The oscillon structure was discovered in a granular system, first seen, and later found in a fluid.
Okay.
And then there was a series of articles where you take the differential equation model and think about the model for other types of problems. Even people have taken DNA chains and found there for some conditions an oscillon type structure. So oscillon's been found in many different situations. That is a localized oscillating structure in a dissipative non-equilibrium system. Yes.
So, often you have like statistical patterns that emerge in natural systems, like, for instance, like the magnitude of earthquake follows a similar distribution as many things in like human systems. Does that kind of tie in with this, or can you maybe comment on that?
Well, no, the understanding of earthquakes, is not complete to be. But there are many phenomena that are described by probability distribution functions which have certain power law behavior, which can occur in deterministic systems, and you can find the same power law for a variety of assumptions. But I don't have much more to say. No, yeah, it's a hard question. Yeah. Yes.
Hi, I'm wondering if you can illustrate more about, what exactly are we looking to answer in this question here? Like, what are we looking for in this general theory of systems that are out of the thermodynamic?
Well, a general theory of non-equilibrium statistical mechanics.
Are we looking for a number?
No, a recipe of how do you approach, if you have a system in thermodynamic equilibrium, you in many cases, most cases, know how to construct a thermodynamic potential function, a free energy, if you like. And then you have an extremum principle. We don't have such for non-equilibrium systems. And when I first started going to meetings about pattern formation in non-equilibrium systems in the 1970s, there was always the suggestion I have a way of calculating the thermodynamic potential that will describe non-equilibrium systems, a general method, but none of those methods proposed has proved to be reliable. Okay. So it's an open question. It's a very difficult question because non-equilibrium systems for the same boundary conditions in a fluid, for example, for the same boundary conditions, you can have multiple solutions. You've got nonlinear systems, so you can have you can have multiple states that occur for different initial conditions that are perfectly robust once you're in that state. So just knowing the boundary conditions exactly is not sufficient to say what the state of the system is.
Nature makes a lot of boundary conditions to control processes, and so there is this chemistry side and biology side that actually will define the final product of the biological structure and material. So what is your opinion on where actually is the boundary between these two strategies in terms of making a materials, biological materials?
Yeah, when I talk to my biologist friends, I get a very detailed biological mechanism with these molecular biology pathways, incredibly complicated. Exactly. So and I don't know where the twain shall meet. Exactly. But I think much more can be done with relatively simple pictures to get some understanding, but that proves how far you can push simple models to understand in general ways different kinds of phenomena is open question. Sorry. Okay.